Okay, the first plenary speaker of this afternoon is José Alberto Cuminato, a great friend of São Carlos, and he is a great mathematician, and besides that, he also has quite influence in the development of applied mathematics and all this kind of mathematics and simulations in São Carlos. And it's a great pleasure to see him, because he is a quite busy man.
Oh, not so much.
Finally, okay, and so let's hear.
Okay, thank you, José.
You are welcome.
Yes. Well, thanks for the kind words. I think this great mathematician is far from what I am, but we strive with the loads of work that we have in here. Well, this presentation I would like to thank José for inviting me here. It's a big pleasure to be in this such a distinctive audience. This amphitheater, or this hall, is very famous for having very great mathematicians, much better than me, you see, making presentations. I've seen even Fields medals and people like that, you know. So it's a great pleasure to be here. And it is also a great pleasure because one of the person who inspired me in something that I'm going to show in the end was Mario Primitiero, who is a very well-known applied mathematician from Italy. And we, sort of 2 years ago, we had a meeting in Rosario, which was Italian-Argentinian joint meeting at that moment in applied mathematics. So Mario was one of my inspirations for this center that I'm going to talk about in the end. So I'm sorry for the advertising that I'm going to make at the end, but being in this audience with many Italians and the long tradition that applied mathematics and industrial mathematics especially has in Italy, I thought was a good opportunity to show you that we're starting something in Brazil, and your help from Italy is very much appreciated if someone is interested in what I'm going to say. This is the only 10 minutes in the end, okay? So I'm sort of anticipating that. Before that, I'm going to talk about this numerical simulation on Newtonian two-phase flow. You see, the simulation in fluid dynamics is getting more and more involved as time goes by, because the problems are getting more and more difficult, right? Despite most of the mathematics of these things are not well resolved in terms of existence, unicity, and the theorems, but the engineers advance the frontier because the problems are there and they need to be solved, they need to be simulated. So many of the equations, we don't know whether there is a solution or not from the point of view of mathematics. Of course, the engineers have a very good, or the physicists have very good reasons to believe that they have the solution, unique and sometimes not well behaved and so on. So this is the sort of simulation that we want to do. You see, the first picture on the left, this one. This is, you know, this is a industrial process whereby you produce most of the fibers that you encounter, all these plastic clothes and all the fibers. This is called extrudate swell. Well, in this case, actually the process is called extrudate, as you might think. So this is a fluid that flows through a nozzle, and then it's a resin usually. So it's usually non-Newtonian, because it's something derivative, something that derives from oil, petrol. So usually it's non-Newtonian. So what is this resin? So as it comes in contact with the air, it solidifies, and then you get the fiber, you see? So this thing keeps pulling, and so you're producing the fiber. But you want the fiber to have a certain diameter. And, but sometimes, because of these viscoelastic properties of the fluid, when viscoelastic fluids have this funny property that it is viscosity many times, depends on the shear stress. If you stress them, the viscosity can increase or decrease, right? It's like the toothpaste is a very good example of fluid which is like that. Inside the tube, this is almost solid. When you press the tube, it becomes liquid and goes out, or not liquid, but it becomes less solid. And then you have all these sorts of behavior. In this particular talk, I'm going to talk about this funny experiment that is very easy to reproduce that. You can do it at home with the, and you see, this is the sort of thing that fluid that when you stir it, instead of forming a depression where you stir it, because of viscoelasticity, it actually climbs the rod, climbs the stirrer, if you like, right? So this is the sort of thing that we're interested in. Well, this is a joint work with, those are two of my former students. Cassio is in Prudente at the moment, and he's finishing his PhD. This is also very interesting because I first met this chap here in this very auditorium 4 or 5 years ago when he came for one of these meetings that they hold here for the what is called initiation, scientific initiation students. They bring it, loads of them from all Brazil in November, I think it is. And then I came, I was invited to give a talk in this meeting, in that meeting 4 or 5 years ago. And then this guy was interested in the problems that I explained, and he went to São Carlos to do his PhD. So that's that's what I said. You see, what is different about these equations? You see, those are the Navier-Stokes equations. Probably you are more familiar with the Newtonian version of these equations. This is the full version. Is when you see, because in the Newtonian, when you write the Newtonian, the equation, the Navier-Stokes equation for the Newtonian fluid, you assuming that the stress tensor has a relationship with the gradient of the velocities. So you substitute this, what is this tau here, which is the tensor, the extra, in the jargon, is called extra stress tensor, right? So what's different here is just that in this Navier-Stokes, I have this term. Of course, I have sort of factored out the Laplacian here, which is the Newtonian part of it. So this is the usual thing people do. People write it, this is extra stress tensor as a Newtonian part plus a non-Newtonian part. Being a tensor in 3 dimensions is a matrix 3 by 3. So you have 9 knowns, right? But because it's symmetric, so, well, from physical arguments, you know that it's symmetric. So you reduce that to 6 unknowns. But then you see, this is this is a scalar equation, which is continuity. And then you have these momentum equations, which, of course, are 3 equations, because they are in the direction of x, or in 3 dimensions, x and y and z. But then you have, you see, as you know, you have the 3 unknowns for the velocities. You have the pressure, which makes 4 unknowns. And then you have these extra 6 unknowns, right? And which makes it 6, 9, 10 unknowns and only 4 equations, right? So to close the system, you have to do, is not this one, all right? This is another thing. But to close the system, you have to do like people do for turbulence. You have to put state equations. You have to basically say how this extra stress is derived or relates to velocity or to whatever, right? So, and this is not even that is well established today. There are many models. People try everything to model how a viscoelastic fluid behaves. So if you look at the literature, there are many, many models. Each model works for some regime, doesn't work for others, and people are in the search of a universal model, if you like, right? A model that would work for most of non-Newtonian, or for all, hopefully, for all non-Newtonian viscoelastic fluids, right? And people are getting closer and closer to that. But the cost of that is including loads of parameters. So you put lots of parameters into your model, and then if you do that, you get something. And if you take the parameter like these and so on, right? But this makes life very, very difficult, because then you have to choose the parameters. And this is not very nice many times, right? So in this particular talk, we are, I think it's probably in the next slide. Yeah. So this is what I was talking about. So I have this matrix, which is this thing that relates to the tau tensor. And this is the equation for the tensor, right? So this is the equation. You see, this is an equation for advancing time for this tensor. And of course, you have many. It's not a simple equation, of course. And then you get this m tau in there. And this m tau is given by that. And then you get all these different models. As I said, the most complete one today is this LPTT. If you set some parameters in here equal to 0, you get the previous one, and then if you set another parameters equal 0, like alpha and lambda, you get the previous one. And this Odroid B is the one that people use in the oil industry, for instance, for modeling concrete. Concrete when before it is concrete, before it's dried, is a very non-Newtonian fluid, you know. If you see, if in these big constructions where they have to pour tons and tons of concrete, you have to model that to see how it is going to behave, even to flow when it's flowing, right? Well, in this talk, then, what I'm going to do is, you see, in addition to modeling this, to solving the equations by, in this case, finite differences, you have all the problems of, because we're talking about, if you notice, I'm talking about two-phase flows. This means that I have, well, examples are, you see, here, for instance, you have the fluid coming out of the nozzle. This is a free surface, but you have the air outside, of course. Then you have to model these two things, you know. So that's why it's two-phase flows. Two flows. You have two flows flowing, right? It's not as opposed to a flow, well, not very much, but if you have oil in the tube, for instance, but not gas. But even when it's confined, you can have a mix of two flows, for instance, or three flows. In the oil industry, it's very common to have oil, gas, and water. It's very, very common. Then the gas forms bubble, the water tries to separate from the oil, and imagine when you pump that through a tube, through a oil, I forgot the name now in English, but these things that they transport oil in long distance tubes, you know? Yeah. Oh, thank you. So this is, in this talk, I thought that the details are there's a lot of details in trying to simulate these things. So I thought that I better just to give you an idea of how these things, how we do these things, and without going into details, especially because I'm not sure whether how specialized the audience is. So I try to just show you more the results of what we've been doing. So in this in this talk, I'm going to talk about 2D, axisymmetric, and 3D flows. Less on 3D flows. We still on this axisymmetric. Axisymmetric means a flow that is symmetric in one direction. So actually the equation is reduced to 2.5, as we call it, right? It's 2.5 dimensions. So because what you do is you have a full equation in, let's say, if it is cylindrical, you have in the r and theta are the 2 dimensions, and then you have the z is this, where the symmetry is, right? Oh, sorry. Finite difference, non-uniform grids, staggered grid. This is a very well-known technique for dealing with these problems. Semi-implicit, because usually in this type of flows, the Reynolds number is very, very low. For those of you who are initiated in these finite differences, when the Reynolds number is small in the Navier-Stokes become very parabolic, or the parabolic aspect of the Navier-Stokes is dominant. So if you do finite difference, then you have the curse of this stability condition, h squared divided by delta t, or delta t divided by h squared. You have to have that bounded by whatever it is. And then you have to have very fine grids in the space dimension, which makes it very difficult. And in the time dimension, sorry. So semi-implicit is a solution for that, if you like. We use projection method, which is a well-known technique for uncoupling the equations, because as it is semi-implicit, you have to solve, because usually what people do in Navier-Stokes, you solve for velocity, and then you plug in the pressure equation, solve for the pressure, and keep it in this cycle. This is what is called projection method. Projection separates these two phases. Otherwise, you have to solve a huge linear system, which is very costly, of course. And then, because these problems are, as I said, 2 flows, you have to deal with the interface problem. And the interface problem is a nightmare for people who are dealing with these things. How to represent the interface between these 2 fluids, and how to apply boundary conditions, for instance, and how to advance these fronts, you know? And you remember, you have to do that, and you can't create mass, for instance. It is very common that when you transport this thing, you either add mass or subtract mass, so that you don't satisfy the continuity equation, right? Well, and then this is something that is quite an innovation here, because the MAC method is well known. We've been working with this. MAC stands for Mark and Cell method. This is a technique for representing interfaces, and is well known for being very versatile in terms of, you see, when you're dealing with moving surface, you can have, for instance, what is called satellite drops. Imagine with a hose, when you're spraying water, you have all the drops, you see, which detach from the main fluid. And you see, imagine how you do that, how you deal that in a computer, right? Because you have to, if you have a representation of the fluid, how you detach things, how do you attach them afterwards. And so the MAC method is known for being versatile in that regard. But it also suffers from other problems, like not being very good on keeping math, conserving math, and well, implementing is not very easy either. The VOF is the opposite. It has some advantages where the MAC has disadvantages and vice versa. So we thought it was a good idea combining these 2 things. And it showed that for these problems, it worked quite well, right? Well, and then probably, see, I understand it's full of jargon here, and perhaps for many of you, these jargons are terrible. This is volume of fluid, this is well, I don't even remember what that is. Well, this is continuous surface force. This is a way of imposing surface tension. You see, remember, I said that you have to represent the surface. In many fluids, the surface tension plays a very important role. Imagine when you have a soap bubble, you know? The surface tension is what keeps it round, you see. But then, you see, you approximating that. And surface tension has to do with the second derivative of the thing that you're approximating. And as you know, differentiating discrete data is an unstable problem, right? Any little change is very easy. Huh? If you take points and you interpolate, it's very easy to see that derivative. It's easy to approximate the function, but it's not easy to approximate the derivative, because any small change in the data can cause a dramatic change in the first and the second derivatives. So that makes it more difficult. Huh? And so those are the things. This is what I mean by semi-implicit method. You see, this is, well, all this tensor is in there, you see. If you see here, I'm discretizing the equation that I showed in the second slide, as you see. This is for the, well, this is for the time derivative. This is, of course, the nonlinear term. And then you have all this, and you know, you see, this is what makes it semi-implicit, because un plus 1 is also on the right-hand side, right? Usually, when it is explicit, you get everything in the right-hand side is in the nth step, right? So here, you have to solve a linear system for every step, right? So what, and also you see, the pressure is there, you know? So this is actually coupled. This is a system that would have to be solved for the three velocities, in this case, and plus the pressure. So this is what, when this projection method comes in, because instead of solving this huge system, what you do is you solve for an intermediate velocity. Notice here the pressure is in the step n. And then I correct the pressure to satisfy the, and then I correct the pressure for satisfying the continuity equation. Because when I do this, the velocity that comes out of that doesn't satisfy that, right? And that is a big problem, because if you don't satisfy that correctly, everything goes wrong, right? So what you do is you put in the previous time step, and then you correct the pressure by finding this psi plus n plus 1, which is satisfy an equation. And basically what you do is you impose on this un plus 1 tilde. No, you write the un plus 1 like that, and you impose that the Laplacian of that, or the curl that is equal to 0, right? Here, this is a detail. I don't think I will discuss that, because you have to, this is just because, well, those are actually how you discretize when you're not using a uniform mesh. Well, the Mach method does that. You solve for the equations, you find the velocities, and then you move the interface based on these equations. So the x position is this is the velocity. You see, you assume that you know the velocities, and then you say, well, now that I know the velocities, then what I'm going to do is move the interface according to these velocities, right? Yeah, and then from now on, having said what I said, I have quite a few problems that we've been trying to simulate. And of course, those are complex viscoelastic phase flows. we hope or we believe that at least until now is a robust methodology. And actually, the problem that we set out to solve 40 years ago was this problem: simulate, not solve, simulate, which is this rod climbing. If you look at the literature, everybody avoids that because it's quite a problem because of, you see, this thing is moving, and then you have this problem of the free surface. Actually, we didn't manage to get to do as we would like, because I would like to do this in 3D. And what we have today is 2.5Ds, as I said, axisymmetric. And as I hope I will have time to show you, this problem is not axisymmetric at all. It is a full 3D problem, right? But we managed to do some of, you see, now it's quite a row of problems that we've been solving. Because of the time, I spent more time in this introduction than I expected. And I would like to show this center for, I think my talk goes up to 2:30. So I have 15 minutes. And I'm just showing you one problem. That is the axisymmetric problem, the rod climbing problem. So this is the video. This is taken from Google. And this is actually what is called the Weissenberg effect, or the rod climbing. So just for you to get an idea of how these things go. And this is done at home. You know, this is a screw driver, and then the fluid is, you know, this thing that you used to make cakes, maizena we call it in Brazil. I don't know what is the name in English, but it's made from cork. So if you, yeah, it's a powder, yeah, it's a white powder that you use for cake. So when you mix it with the water, it produces a viscoelastic fluid, right? So you've seen it, and then you see, well, I have some other problems, but well, this is the mesh, and this is comparison with what is in the literature, how far it climbs. So we have numerical experiments. This is it's experimental data from quite old ones. And then here, this is when you have xi equals 0. This is the completely, I think the xi equals 0 is the, I don't remember what it was. But you should concentrate in that. It's just that to showing these different works. And as I said, there are not many people that solve these problems. And it compares quite well with the experiments, at least as far as we can go. So we have many of these things. And one thing in the literature, this Weissenberg number, as you increase it, things get very, very wetty, you see? So in the literature, people don't go with this number beyond 1 or 2. And this code, I think, is managed to go up to 5. And then there are numerical results based on formula, how far this goes. And this is that straight line here as a function of this wi squared. So I'm plotting against wi squared. So it's actually a straight line. So it's a straight line, and this is wi squared. And that formula, of course, is only for wi very small. You see, in applied mathematics, you have to resort to everything that is available in order to try to convince yourself that your code is working well, not perfectly, but at least is reproducing the results that you know are true, because you're never sure whether these things are true or not, right? And so that formula is only valid for small wi. So for the small wi, we plot again the analytical prediction against the several works, and you see these squares here are is our work, and then you have the other works in the past, and then this is the experimental. You see, the experimental is quite good apart from this. Oh, no, this is, of course, is the legend. But you see, the experimental fits quite well to that, right? So you see this, and then you see when you increase this Wi, you get these different regimes. This is what is called breathing in the literature. And what happens is that the thing climbs up to one point, and then the weight gets too heavy, and then the gravity brings it down again, and so it's a sort of a periodic movement. And then this one climbs in a spiral, this nautilus. And of course, rupture is when this goes so fast that actually the fluid flows from, flies from the rod, you know. And if you drive it fast enough, right? And well, this is again the simulation. And I can show you. I'll show you just one simulation of this is, and then I'll go on for the next one. This is a simulation for the fluid, you know. This is when the revs here, the revolution, because the Weissenberg number increases with the revolution, with the velocity. So
that was assuming symmetry?
Yeah, assuming symmetry, yes. And then the other one is, I think it's faster revolution. And then you see that it climbs higher or something. You see the breathing thing, which goes. We believe that's the first time that someone has been able to simulate this breathing thing. Basically because the code doesn't work when the Weissenberg number climbs too high, you know. I think I'll stop there, you see, because otherwise I'll go beyond my time. And I would like very much to show you what we've been doing with this center. So I will stop here. And if someone has some question about this, I can answer now. And then I'll talk about the center for the last 5 or 7 minutes that I have left. Yes?
This is partly a remark, but I know what we often do with soap bubbles using the brachievolver is just let the surface try to reduce its perimeter instead of trying to figure out the tension or force direction that depends on the second derivative.
Right. Well, so what is your question exactly?
Well, so have you tried ways to avoid using the second derivative?
No.
So that you don't get
No, we haven't. No, the modeling is the usual model for surface tension, you see? It's a coefficient times the second derivative, right? That's because this CSF, because you see, you can't, some things you have to assume and use what is in the literature. It might be what he's saying is better than what we've done, but some of the things is probably this is a way of looking at it and for future work. Any other question or remark or? Well, if not, I'm going to show you these. Oh, how do I expand this? Oh, yeah, I have to go down here. Sorry. Oh, yeah, that's it. Right. So this is this center that we've been establishing in San Carlos for the last 3 years. And the idea is the following. As you all know, and here we are in the main institution that promotes mathematics in Brazil, right? We have recently have these Fields Medal and so on. But in my opinion, looking at the world, including Italy, Germany, all the countries, in all the developed countries, mathematics plays a very important role in the 3 aspects, which is, of course, reproducing in the schools, And this SBM in Brazil is doing very well. And then you have the theoretical mathematics. And in my opinion, you also have one leg of this thing, which is this, how mathematics translate into wealth, right? And we in Brazil, in my opinion, we didn't quite grasp that aspect of it yet, right? So we are very academic. If you ask most of the students doing PhD in Brazil, what do you want to be when you grown up? The reply will be, I want to get a job at some university, right? And this has been successful because being a country where we still lack lots of university, and they've been created in last years, so academic jobs go on all the time, so they get employed. But as you all know that come from Italy, from Germany, from the States, this is not true forever. One time this is going to stop, and the mathematicians will not find work in academia, right? So in my opinion, we have to create a market for these PhDs of the future. It might be we're still far away, you see, it might be. If you look at the Brazilian status of development, it might be we still need loads of universities around, it might be we do. And still this academia is going to need it and so on. But I think it is, in one stage, even society is looking at us and say, well, look, you mathematicians, what the hell wealth you produce? So in my opinion, you need that. And because of that, I set up, tried after I, now that in my decadence, if you like, I could spare some time to put into that, right? So that I don't need more publishing many papers and I don't need to supervise many students, so I could put a lot of time to that. And I'm putting a lot of time to that in the last 3 years. And so I set up this center, which I call Semiai. And it started, Semiai means Center for Mathematics Statistics Applied to Industry, right? But then I thought that was, and then this word in Portuguese is quite appealing, because Semiai means throw the seeds, right? Spread the seeds, right? So I thought that was a good acronym for what I was trying to do, right? But then we changed it to, because then I thought that it's not only mathematics and statistics. I think it's something more general than that we need to use, which is what I call now mathematical sciences, right? And in mathematical science, of course, statistics is one of them, and so is computer science. One side of computer science, you know, especially this computer science, which is linked to what I said here. You see, in this code, in this simulation that I showed here, there is a lot of computer science, you see. A lot of data structure, data, dealing with data, you know, how to store this data, high performance computing. You see, most of these problems doesn't run in a laptop. You have to do it in so many cores, as people do it today. So I don't want to go on very much over. So, you see, and then, well, this is all this thing that I said that mathematics in Brazil is quite, you see, this is a production in terms of papers, you see. This is a survey that this newspaper, Folha de São Paulo, did a few years ago. The papers in Brazil get 128 citation per and then in the world, the average is that. So we're quite close to the average. You know, of course, the average is not the best, but at least we're not far to that. And mathematics is the area that we closely to that. You know, so and then we have these centers. But my time is running up. So this was started in September. In 2011. And then we just started this center as an idea inside the university. We didn't have a budget, anything like that. And then soon the events from there worked in my favor very much, because when we just started that, and then the university put a proposal forward for people put up money for people putting proposals for centers. And then we put a proposal for 1 million reais, and we got it from the university. And that helped me. 2 years after that, FAPESP, which is the funding agency in the state of São Paulo, they run this big proposal for grants to run what is called CEPID. CEPID is a center, right? They only finance 15 of them in all the areas. It's a competition. It took 2 years to do all the process, you know? And Matemática never even applied for one of these grants. Ours and Galvez, who is a friend of mine in São Paulo, he put forward an innovation center in neuroscience, and he got it too, right? So this time we had 2 centers. We competing with all these health diseases, with all these diseases that we have, Brazil, Zika, and dengue, and we managed to get the money, the funding. So this center now is funded. The main 4 groups, as I said, FAPESP requires that we have groups around things, and despite that idea of industrial mathematics doesn't fit that picture very well, because usually problems from industry, many times they are very interdisciplinary. You cannot say, well, this is only the optimization, this is only, usually it includes optimization, free dynamics, biology, and so on, you know. But, you know, you have to fit to how the structure goes. So our main groups are those applied optimization with the group in Campinas. You probably know very well Martinez and all his group. Computational free dynamics, which is my group, and people in São José dos Campos. Oh, it's not that direction. And then risk assessment, this is the statisticians come into play. And this is, of course, the part of computer science that is more mathematical, with database and the big data and things like that, intelligence, software engineering, right? Well, those are I just want to rush because just to show you some of the problems that we have. This is a problem in optimization, molecular dynamics. This is a code which is in the internet, and it reached many, many thousands of hits since it is launched. It is a free software. One of these, you know, and then in fluid dynamics, we have projects with the Army, with the big companies, energy companies. You see, it's amazing how these things work. Because when I started this, I thought, well, my goodness, I will have to rush after these people. And after 4 years, we do get the phone calls from people say, well, look, we're trying to solve this problem. Can you help or something? You know, it does work. I think I will stop there. I don't want to go beyond my time, because otherwise you see, this is a very successful one, which is coming to stream soon. Nowadays, the thieves in this country are very, very clever. Everything the banks do, they manage to break. And so the things that are coming soon in the cards is it is possible to, you have a pattern. How hard you press the key when you press the keys in the machine for the credit card, you know? You have this, how fast you do it and how hard you press it. This software is already being implemented by 2 banks. And soon this is going to be one of the thing that, of course you're not going to know it, but behind the thing is, this one, in addition to the numbers, of course, to the key or the password that you use, there's also been, even if the guy discovered the discovery of password, if he doesn't repeat exactly how fast and how hard you press the keys, you're not going to get it, right? So, well, I think that's it. Thanks very much.